Okay, so good afternoon, everyone. And the talk is about deep dive into the scheduler in Apache Spark. So first, I will introduce myself. I'm a software engineer at Databricks, and my name is Xingbo. So I'm currently an active contributor of Apache Spark. And my interested areas vary from Spark Core to Spark SQL. Please let me introduce Databricks. And Databricks is founded by the original team who created Apache Spark. We provide a platform that accelerates innovation by unifying data science, engineering, and business. We unify data engineers and data scientists by collaborative notebooks, and we unify data and AI technology by Databricks runtime. And we eliminate infrastructure complexity over the cloud-native service. Okay, so feel free to try with Databricks Cloud. So first, let's begin with the basic architecture about the Spark core module. Actually, when we launch a Spark application, we first start a Spark contact. Spark contact is the main entries of user jobs. So when you start a Spark contact, it will initiate a pair of TaskScheduler and the SchedulerBackend. The TaskScheduler is responsible for scheduling tasks, which we will focus on that in this talk. And the SchedulerBackend is focused on the cluster resource management, which we implement both locally and with a cluster mode. So the Spark contact, as we mentioned before, is the main entry point, and it provides the API for users to submit a job, to cancel a job, and it creates SchedulerBackend and the TaskScheduler and the TaskScheduler initialization. So here, let's see what it happens when we submit a Spark job. So the scheduling process starts with RDD objects. We first build operator as a DAG called DAG, or the Directed Acyclic Graph. Then the DAG scheduler splits the graph into stages and submit each stage by ready. That means when each parent of the stage is ready, we submit a new stage. And the task scheduler is responsible for launch tasks and manage the process and return the results or retry on failure. And the workers actually execute the tasks and store and serve the blocks that we generate and we consume on each task. So let's begin from a simple example that RDD1 performs a join action over RDD2, and then the result is grouped by some column, and finally we filter with some predicates. So when this RDD is transferred into stages, we can see that the join operator produces a co-grouped RDD, and that contains a shuffle dependency. So another shuffle RDD is generated by the group by action, and the filter action is transferred into a map partitions RDD. So this way, your command becomes a chain of RDDs, and then we have to divide the chain of RDDs into separated stages. The way we split them is that we split RDD chains before the shuffle RDD and after the shuffle RDD to different stages. So what is a shuffle? A shuffle is quite like a reduced task. It splits the input files and distributes them into new partitions. So let's see, what does a TaskScheduler do? A TaskScheduler splits graph into stages and submit each stage by ready. So a stage is a set of parallelized tasks all computing the same function that need to be run as part of the Spark job, where all the tasks have the same shuffle dependencies. So each stack of tasks run by the scheduler is split up into stages at the boundary where shuffle occurs, and then the TaskScheduler runs these stages in topological order. So the TaskScheduler implements stage-oriented scheduling. It begins with computing a deck of stages for submitted job, and it keeps track of materialized RDD or stage outputs. And finally, it finds a minimal schedule to run the job, and it turns the stages into TaskSets. Here is an example of a chain of stages. We can see that stage 2 have dependency over stage 0 and stage 1, and stage 3 depends on stage 1 and stage 2. So on submitted job, we first compute stage 3 and find that it have a parent stage that is not ready, and then we turn to stage 2 and found that it actually depends on stage 0 and stage 1. So we first submit stage 0 and stage 1, and after they are finished, we submit stage 2. And after stage 2 comes successfully, we submit stage 3. So in this way, we can avoid to compute stage 1 for multiple times, which is ideal. So in the last presentation, we mentioned that we will compute stages. So how do we compute a stage? Actually, each stage is computed with our conception called TaskSet. A TaskSet is a set of tasks submitted to compute the missing partitions of a particular stage. And normally, a stage only submit one active task set. But when we count task failures in, a stage can correspond to multiple task sets. So here we can show an example of one active task set can fail. One reason is that one or more tasks in the task set can hit a fetch failure. A fetch failure is when a task want to fetch some shuffle data, and it found that the shuffle data is not there. So this is called a fetch failure, and the task can't proceed. So the task fails, and the task set is marked zombie. And the other ways a task set can fail is that when all available slots are blacklisted, so you can't schedule any new tasks on that, or there are some exceptions while we do task serialization, or exception while we get task result, or other exceptions. And a zombie task set can have one or more tasks in the task set to be in the state of failure, and the other tasks can still be running. The only major difference is that we don't launch new tasks for zombie task set. So here we can see that one stage can correspond to multiple task sets, and we only need one of these task sets to finish successfully to complete a stage. So here we will show how we schedule tasks among task set and within a task set. We use that basically with a task scheduler. So a task scheduler actually works like the deck scheduler submit a set of tasks to task scheduler, and the task scheduler schedule and monitor tasks with SchedulerBackend, and it returns the events to deck scheduler. For jobs, there are job submitted and job canceled, and for stages, there are map stage submitted and stage canceled. And for a single task, there is a completion event. Either the task finished successfully or the task ended with a failure. So currently we schedule tasks in a batch scheduling way. That first we get all available slots for us to use, and then we schedule tasks with locality preference on them. To launch machine learning or deep learning workloads, we are proposing another barrier scheduling approach, which is discussed in the Directed Spark 24375. And the general idea is that we want all tasks in the same task set to be launched together. So we just wait until all tasks in the same task set can be scheduled at the same time. And when we get a task failure, we just retry all tasks in the same task set. So how do we schedule among multiple task sets? By default, we can do it in a FIFO way. That means the earlier the task set is submitted, the earlier it gets executed. That should work for the common case, except that when we have multiple users which run jobs on a single shared cluster, in that case, we may see that we have some long-running tasks that block later tasks because the long-running tasks are submitted earlier. So they keep running and keeps seizing the free slots, and the tasks submitted after it may have to wait until the long-running task finishes. So this is not ideal. And to address this issue, we proposed another option called fair scheduling. The fair scheduling is trying to ensure that we give minimal share of resource for each user. So each user can get a minor share of the cluster resource for their tasks, and they won't be blocked forever by other long-running tasks. So there are basically two ways to schedule between task sets. The first is that we do FIFO over task set managers, and we order tasks by priority, which we set as a config. And if priority are the same, we may need to sort by stage ID, where we submit a list of stages which don't have dependency on each other. And under this case, the priority are the same, so we sort by their different IDs. And for fair scheduling, actually we put all the resources in the cluster in a pool, and we can divide the pool further into different children pools. So we can do fair scheduling between pools, or FIFO, or fair scheduling within pools. So when we try to do fair scheduling, we try to launch tasks in a task set that is further below the minimal share. So you always launch tasks for users which is using less of the computing resources. And if both task sets are running above the minimal share, we just order them by the weighted number of currently running tasks to hope them finish earlier. So after we have chosen that which task set we want to run, how do we schedule different tasks or a single task set? The general idea is that we try to achieve better locality for each task because better locality implements less data transfer over network. And it also implements a higher transfer speed over network. So both lead to a higher performance. We have different locality levels. For example, we have process locality, which we can access the data in memory or in the cache. We have node locality, in which way we can access the data on local disk, or rack locality. Even we can't achieve to load data on the single node. We can let the data transfer inside the same rack, so we still get a higher transfer speed. So the task set manager is responsible to schedule tasks within a single task set, and it implemented locality-aware scheduling called delay scheduling. So before we go into detail of the delay scheduling, we explain two general ideas that we want to achieve better locality. The first is that we wait for tasks to finish with us queue running tasks to assign slots to new submitted task sets. We wait for tasks to finish because running tasks may have finished a significant amount of works, and most tasks don't take quite a long time to finish. The second is that we wait for a few extra time to achieve better locality. Because that we, after some modeling and computing, we found that with waiting for a few extra time, the possibility of achieving great locality becomes exponentially increased. So here is an example how the delay scheduling works. First, we have a sequence of pending tasks, and when we have a free slot called let's call that slot 1, then we try each task on the slot 1 and to see whether the locality satisfies the max locality required. And if the answer is yes, we just launch the task. It's perfect. We achieved great locality. But if not, we tend to see whether we have waited we have waited longer than the wait timeout. If it's yes, it means that we have waited for a few times and we haven't achieved great locality, so we just decided to not to wait anymore and launch the task anyway. And if we haven't exceeded the wait timeout, we just skip current scheduling and wait for another round of scheduling. So this is field code of how delay scheduling is implemented in Spark. You can see that when a free slot is available, we compute max allowed locality for pending tasks. And if there exists one task that can launch with with a locality that is, satisfies the max allowed locality, then we just launch that. Otherwise, we check whether the wait time is larger than the max delay time. And if the wait time is larger than the max delay time, we just launch the task. Otherwise, we wait for next round of scheduling. So for more detail of delay scheduling, you can check Matei's paper. Yeah. Delay scheduling, a simple technique for achieving locality and fairness in cluster scheduling. So handle failures is another important topic for scheduling. For regular task failures, we believe that a failed task can finish successfully on another retry run. So based on this understanding, we just record the failure count of each task, and if it haven't failed for multiple times, we just retry the task. And if the failure count of the task have exceeded the max task failures, we will know that something is broken, and we have to abort the whole stage and the corresponding jobs. This is a different case for fetch failure, which happens when we try to fetch a block from some address. So when a fetch failure happens, it is likely that some shuffle data are lost, and we can't recover from that. So instead of retry the failed task, we just retry the whole stage. So how do we retry a stage? Actually, for this example, result task 1 is trying to fetch shuffle 1-1, and it hit a fetch failure. And in this case, other shuffles, I mean the shuffle 0-1, shuffle 0-2, and shuffle 0-3 are not on the same host with shuffle 1-1. So we just retry result task 1 to finish the stage retry. And for another example, unfortunately, shuffle 0-2 is on the same host with shuffle 1-1, and fetch failure of shuffle 1-1 can mean that the host have been go down. So shuffle 0-2 is also lost. And in this case, we have to first retry the shuffle map task 2, and after it finished successfully, we retry the result task 1. So for retry task, we just retry parent stages if necessary, and we only retry tasks that have missing partitions. For retrying TaskSet, we just mark current TaskSet as zombie, and we don't kill running tasks to hope them will finish in the future. So for cluster managers, actually, the cluster manager is implemented in SchedulerBackend, and it manages resources to schedule tasks on. We provide a local mode, local cluster mode, and a cluster mode for SchedulerBackend. A local mode is when your driver and your executor work in the same progress, and it's used for running a task on your local node. The local cluster mode also have driver and workers run on the same process, but the executors are run on different processes, still on the same single node. And the cluster mode is used most for production environment, that we run different executors on multiple nodes, and we may run driver on a separated driver node, or we can run driver on a worker node. We have implemented a standalone resource manager for Spark itself to manage resources. We also support external resource managers, and the currently implemented external resource managers are Mesos, Yarn, Kubernetes. So the workers actually execute tasks and store and serve blocks. The worker is a container for executors, and it provides threads to run tasks. And it provides a block manager to store and serve blocks. It is also optional to start the external shuffle service, which can continue serve blocks even when the executor has exited. So so at last, I want to give some tips to improve your job performance. The first is that we may break long-running tasks into simple or short tasks. The major reason is that in that way you have more chance to have available slots, so you have more chance to schedule for pending tasks and to achieve greater locality. And another reason is that a simple or short task may cost less during recovering from failure. The second tip is that we may broadcast small hot input files, because when you have multiple job or tasks need to read from the same data file, and unfortunately, the data file is small, so it only presents on a small fraction of nodes. And under that case, you can't achieve greater locality, so you have to broadcast your small hot input files, and you can achieve at least node locality for every task you launched, and that will quite greatly improve your performance. So that's all, and thank you.